Hi, Chemistry. Mrs. KJ here, going over lesson 1.11. Review ideal gas laws. Review concepts presented in the lessons, the ideal gas law and absolute zero. In separate laws, Boyle, Charles, and Gay-Lussac describe the behavior of the variables of a fixed amount of gas, including pressure, volume, and temperature. Avogadro later introduced a fourth variable, the amount or moles of gas. Clapeyron derived one general equation, the ideal gas law, to describe the behavior of gases. From this one equation, Kelvin determined the universal gas constant and introduced the concept of absolute zero. So, universal gas constant is abbreviated what letter? Capital R. And what happens at absolute zero? The motion of atoms and molecules stop. All right, objectives. Solve problems using the ideal gas law in the form PV equals nRT. Apply the ideal gas law to calculate the number of moles of a contained gas. So contained meaning that it's in a container. Solve problems using the ideal gas law. Compare and contrast the properties of a real versus an ideal or perfect gas. Convert a temperature in Celsius to the Kelvin scale, and we do that by adding how much to the degrees Celsius? 273. Interpret graphical information about temperature in Celsius and kelvins. Describe 0 Kelvin as absolute zero. Describe the relationship between average kinetic energy and temperature. So, the more movement, the more kinetic energy, the temperature? Higher. Show that Kelvin temperature is directly proportional to the average kinetic energy of the particles of a substance, and apply the combined gas law to calculate temperature, pressure, and the volume of an enclosed gas. All right, so you can always go into the lesson to get the lesson guide. All right, review ideal gas laws. So we're going to be doing a review. Ideal gas law mathematically relates pressure, volume, temperature, and the amount in moles. Boyle's law, Charles' law, and Gay-Lussac's law can be combined into one equation, the combined gas law, where PV over T equals a constant K, or the way we would use it, your original pressure and volume divided by temperature equals your final pressure and volume divided by temperature. Avogadro's law states that at the same temperature and pressure, equal volumes of gases will contain the same number of atoms or molecules. So volume divided by the number of moles equals a constant K. All of those gas laws are combined into the ideal gas law, PV equals nRT. The SI or metric universal gas constant is R equals 8.31 liters kilopascals per mole Kelvin. And of course, if we use ATMs instead of kilopascals, then we have a different R value. Real gases and ideal gases behave similarly, except under extreme low temperatures, so close to absolute zero, and extreme high pressures. So for the most part, being on Earth under common circumstances, we can use PV nRT to a pretty high degree of accuracy. Absolute zero, temperature is a measure of kinetic energy. Kinetic energy is motion. Temperature is measured in degrees Celsius or Kelvin. The coldest temperature is absolute zero, which is colder than outer space. And even scientifically trying, we haven't quite gotten that cold. Kelvin is directly proportional to the average kinetic energy. Molecular motion accounts for the properties of gases, so the fact that the atoms are moving is why gases are the way they are. Molecules move, and thus they have kinetic energy. Heating or cooling gases changes the average kinetic energy of its particles. Temperature is a measure of the average kinetic energy of the molecules. So if you have a thermometer, let's say the word temperature is our thermometer, the more often it gets hit by the molecules, the higher the column of alcohol or mercury rises, and the higher the temperature. All molecular motion is believed to stop at absolute zero, 0 Kelvin, and nothing can be colder. Absolute temperature is measured in kelvins. The physical properties of substances at low temperatures have interesting applications, like the supermagnets, superconductivity, so they don't lose energy to heat, which saves money. All right, so we have the ideal gas law. Ideal gas law mathematically relates pressure and the amount of moles and two other things, one of which is measured in Kelvin. So it's measured in Kelvin, your degrees Celsius. So besides relating, oh, not degrees Celsius, temperature. There you go. It's measured in degrees Celsius. And besides the ideal gas law relating pressure, temperature, and the amount, it also relates what? The volume. And the ideal gas law mathematically relates temperature. It's measured in kelvins. The coldest temperature is absolute zero, and it's directly proportional to the average kinetic energy. Ta-da! All right. And now we need to do the problem set. Problem set 56, the ideal gas law. There we go. Let's make this a little bigger. The objective, use the ideal gas law to solve problems involving changes in pressure, volume, temperature, and the number of moles of a gas. The ideal gas law. The ideal gas law combines the laws of Charles, Boyle, Gay-Lussac, and Avogadro into one law. This one law relates pressure, volume, temperature, and the moles of gas. Remember that Boyle's law describes the relationship between pressure and volume of a gas. Charles' law describes the relationship between the temperature and volume of a gas, and Gay-Lussac's describes the relationship between the temperature and pressure of a gas. However, each of these laws applies only in specific solutions. For example, Boyle's law cannot be used to determine the pressure of a gas if both the volume and temperature are changing. Scientists use a more complete gas law, the ideal gas law, to describe the relationship between temperature, pressure, volume, and the number of moles of a gas. The ideal gas law can be written as PV equals nRT, where P is pressure, V is volume, N is the number of moles, T is temperature in what unit? Kelvin, and R is a constant called the gas constant. Like the other gas laws, the ideal gas law can be written in a form that allows the calculation of the results of a change. So we could also have P1V1 over N1T1 equals P2V2 over N2T2. All right, determine the effects of a change in pressure and volume. A 2.5 mole sample of a gas has a temperature of 729 Kelvin, a pressure of 3.00 atms, and a volume of 3.8 liters. What will the new temperature of the gas be if the pressure changes to 2.20 atm and its volume changes to 5.4 liters? Assume the amount of gas is constant. All right, so make a list of everything you know. And what are we solving for? We're solving for T2. Go ahead and hit pause and work through this entire equation on your own. So we're going to use the equation P1V1 over N1T1 equals P2V2 over N2T2. So if you didn't get that far, hit pause now and finish it. Now, our number of moles did not change, so it's going to be 2.5 in both of these formulas. And the ends cancel out, which is giving us the combined gas law. If you left them in there, that's fine, but you could have taken them out. So now we have that formula. We rearrange it algebraically to solve for T2. And you can see our ATMs cancel, our liters cancel. We're left with Kelvin. And our answer is 7.9 times 10 to the second, or 790 Kelvin. All right, let's go back and check our remembers. Remember, an ideal gas is a gas made up of particles that are infinitely small and do not interact with one another. Ideal gases do not exist. However, many real gases behave like ideal gases under common conditions. So we can pretend they're ideal, basically, because we are not working at absolute zero or crazy high pressures. The ideal gas law is an idealized relationship between pressure, volume, temperature, and number of moles of a gas. It gives exactly correct results only for an ideal gas. However, the ideal gas law, like Boyle's, Charles, and Gay-Lussac's laws, can give reasonably good results for real gases under conditions in which the real gases behave like ideal gases. All of these gas laws work reasonably well for many real gases under common conditions. In other words, good enough. In general, real gases deviate most from ideal gas behavior at very low temperatures and/or high pressures. Tip, remember you can only use the version of this if the number of moles what? Stays constant. All right, calculate the value of the gas constant. Use the ideal gas law to calculate the value and units of the gas constant R. So, collect and strategize. The ideal gas law can be written as PV equals nRT. At STP, 1 mole of a gas has a volume of 22.4 liters. STP, again, is standard temperature and pressure. And it is 273 Kelvin and 1 atm. From this information to solve for R by rearranging the equation and substituting, so they're saying you can actually calculate the R value because we know everything at STP, and we want to find the R values for atms. Remember, if the pressure value is kilopascals, then we can use the one on the previous page. We can use the R equals 8 point something. Oh, it was in the previous lesson, 8 point something. But because we're doing ATMs, we're going to have a different R value. So do the math, hit pause. What do you get? Now, if you're using ATMs for your pressure instead of kilopascals, your R value is 0.0821 liters ATMs per mole Kelvin. All right. Example number 3, calculate the number of moles of a gas. A sample of a gas has a temperature of 309 Kelvin, a pressure of 1 atm, and a volume of 2.05 liters. How many moles of gas are in the sample? Hit pause, get your answer. This problem does not describe a change in conditions. So if it's a change in, then we need to use that P1V1 equals P2V2, or if it's all of them, then we need to use the combined gas law up here. But since we just want to find the number of moles for a set condition, we can use PV equals nRT, and that's the form of the ideal gas law to solve this problem. So if you didn't get that far, hit pause and do it now. Make a list of everything you know. We have to use the R value 0.0821. Why? Because our pressure is ATM, and that's the R value, the constant, when you use ATMs. So if you didn't do that, hit pause, get your answer again, and we should get 0.0808 moles. Again, our liters cancel, our ATMs cancel, our kelvins cancel. Remember, because this is a fraction underneath a fraction, and so this Kelvin technically goes to the top, and so does the moles. I did show that in the 1.09 lesson, I believe it was. If you'd like me to explain that mathematically to you again, please do not hesitate to contact me. Example 4, calculate the pressure of a gas. A tank of oxygen gas contains 32.5 moles. The volume of the tank is 50.0 liters. What is the pressure of the oxygen in the tank when the temperature is 294? And go ahead and get your answer in atmospheres, ATMs. So hit pause, get your answer. Tip, as with all gas law calculations, calculations involving the ideal gas law or the combined gas law must include temperatures in Kelvin. Okay, so you make a list of what you know. We rearrange to solve for P, our pressure, and our answer should be 15.7 atms. Make sure you use the correct gas constant. So not the one that's 8 point something. That's if we use kilopascals. We're using ATMs, so we have to use the R value of 0.0821. Example 5. A chemical reaction produces 52 liters of dichloride gas at STP. What would the volume of this gas be at 155 Kelvin and 2.5 atm? Hit pause, get your answer. Collect and strategize. Because the number of moles of gas does not change, the combined gas law, which is P1V1 over T1 equals P2V2 over T2, can be used to solve this problem. And we need to use the following information because STP is 273 Kelvin and 1 atm. If you didn't get this far, hit pause and try it again. We rearrange and solve for V2. Put in your answer, and you should get 12 liters. And we will continue this lesson in the next recording.